Good morning, everyone. My name is Carlos Racines. I'm a student of the University Catholic of Guayaquil, and my topic is troubleshooting PCB and electronic product design with thermal imaging. So I'm gonna start with the definition. Okay, is a device that creates an image using infrared radiation, similar to a common camera that forms an image using visible light instead of the 400 and 700 nanometer range of the visible light camera. Infrared cameras are sensitive to wavelengths from about 1000 nanometers to about 40,000 nanometers. The art of capturing and analyzing the data they provide is called thermography. Application. As electronic circuit boards and components get smaller and more powerful, indirect heat can cause significant damage. Infrared thermography can identify the hotspots, allowing for improved thermal management and greater advance in circuit board design. Electronics don't like it hot, that's why electronic system designers are looking for ways to keep their components cool while the sizes of their device shrink. And it's important that you can also want to know that finding and fixing hotspots in electronic R&D is a guessing game if you are not working with a thermal imaging camera. FLIR infrared IR cameras for research, development, and science allow you to see temperatures across an entire target, so you can quickly identify heat dissipation problems and begin working on solutions. Pros and cons. The pros. It's important because today infrared cameras offer up to 17 times the resolution of camera used 10 years ago for nearly the same cost. And this kind of technology have a lot of application because all of the industries work with the electronic devices. And the cons. One challenge to thermal imaging is correcting for surface emissivity. Many electronics boards have components with varying emissivities, some of which are Chinese and therefore have a low emissivity. This makes them for challenging to measure for absolute temperatures. Issues applies in Ecuador. The use of technical cameras to detect errors in PVC and electronic products is a great help. Since the country the process industry, they use very frequently materials that with the help of thermal cameras can detect faults and avoid wasting time and money. And the conclusion. For me it's very important this technology because can saving a lot of time in process of our devices, can detect some mistakes, and this most of the cases in a quickly way. And it's important because most of the enterprise in this country and around the world they need to saving time because for these enterprises time is a lot of money, and this technology have a lot of application because work with essential parts of an enterprise like a device productions. So we're gonna show these 5 videos, so it's very interesting because it's the same topic. Thank you.
Hi, my name is David too, and we're in this electrical maintenance room to show you how to use a thermal imaging camera to do some electrical panel inspection. So I have here the Agilent 5855A thermal imaging camera, and we're going to go over here to an electrical panel and take a look at it. So here's my electrical panel, and all I'm going to do is I'm going to point my thermal imaging camera at the panel. So what you can see is there are a few hotspots that we're interested in taking a look at. So right now I've got this max reading that tells me that particular spot is measuring about 30 degrees Celsius, but it is a lot hotter than all the other points on my panel. So if I was an electrical maintenance worker, I'd actually might be interested in taking off this panel and inspecting those wires, or maybe tracing the circuit and figuring out why it's so hot. One other thing I wanted to show off is maybe from this thermal view, you can't actually see which switch I'm pointing at. So I'm going to turn on this laser pointer by just holding down this star button, and now you can actually see what breaker I'm actually pointing at. So that's just another way to help you make easier thermal measurements with your electrical panel. Thanks a lot.
Hello, my name is Roberto Poyato, and today I'm going to talk about inspecting electronic boards with an infrared camera. Electronic devices are around us, and every day their electronic components are more sophisticated and complex, so the energy they consume is more concentrated in a specific area, which also produces a concentration of heat that must be dissipated. So, thermal dissipation is a key aspect for the proper operation of electronic components. In this video, we can see how an electronic board heats up when it is fed and how the temperature of each electronic component is increasing till the steady condition. So, after reaching a stable temperature, we can analyze each of the integrated circuits of the electronic board. As electronic components can be very small, we need to consider what are the key parameters of an infrared camera so that we could detect problems properly. In this sense, there is a parameter of the camera denominated IFOV, that is, the instantaneous field of vision, which is the parameter that indicates the minimum object size that we can see at a certain distance. The IFOV depends on the number of pixels of the sensor, but also on the type of lens of the camera. In this case, we are using a TI400 with a sensor of 320 by 240 pixels and the standard lens, which offers a nice IFOV of 1.31 milliradians. Additionally, we should keep in mind the minimum focus distance so that we could be as near as possible to the components. In this sense, for example, it is possible to use a macro lens that would reduce the IFOV, that is, would improve the IFOV, and also would allow to work at smaller distances so that we can see more details.
How does thermal imaging work? Thermal imaging is used by firemen and law enforcement to save lives as a result of its ability to see through smoke and trace body heat. But how is it possible that thermal radiation can be used to detect heat? Well, let's doodle it out. A thermal imaging camera features a unique lens that allows infrared energy to pass through it. Then, the focused light hits a sensor that scans the information and draws from several thousand points in the field of view. Through this process, an intricate temperature pattern known as a thermogram is created, which only requires 1/30th of a second to develop. The thermogram then transforms into electric impulses, which are directed to a signal processing unit that translates the information into data for the visual. The created image displays as various colors that correlate to the amount of infrared energy emitted. It is this combination of elements that generate the image that emergency professionals rely on, not only to protect us, but them as well.
Hello, my name is Michael Stewart with Fluke Thermography. Today we're going to use thermal imaging to inspect a common electrical motor for issues that might be impacting energy usage. So I've done a little bit of prep work. We'll show you what we've done when we get over there, but the first thing you always need to have is proper equipment. Make sure you have a thermal imager, it's powered up, ready to go. Make sure you have proper personal protective equipment. Here we have an electrical motor coupled to a pump. The work that we've done in advance, obviously you can see that we've removed the shroud over the coupling and we've removed the cover over the junction box or the termination box. Need to have direct line of sight with thermal imaging in order to do a proper inspection. The first thing that I generally like to do is I'll take a look at the overall motor, the housing itself, and I'll be looking for unusual hot spots or localized hot spots that I wouldn't expect. In a normally operating motor, you would expect nice even heating and distribution across the entire housing of the motor. If you see anything that's off, that could be indicative of a problem. Likewise, if we look at this motor and it's running a lot hotter altogether over the entire motor housing, that's an issue as well. So let's take a look first and see what we find out. Looks quite even, I don't see any issues there. You know, obviously, if this motor were running hotter than usual, that could be an indication that perhaps the cooling fan's not working properly. It's not aspirating properly. I think everything's working okay here. Number one, because the temperature is good. Number two, the fan is operating. If I do find a localized hot spot, that could be indicative of a problem with one of the phases. Maybe some of the windings are burning out. Too much heat will destroy that insulation. Could also be an issue with transients on the line, could be a problem with harmonics on the line causing unusual heating. Either one of these situations, the overall overheating or the localized overheating, can cause that motor to work a little bit harder than it needs to. It will draw more current in order to compensate for the problems that it has, and that will impact your bottom line and your energy usage. Next thing that I'll move on to is the electrical itself here in the termination box. I'll look for high resistance connections. So I'm not seeing anything here, but if I were to see a high resistance connection, it could be too loose, too tight, strands broken on the line, something like that. That will dissipate some of the electrical energy you want to actually make the motor work, and it will dissipate it as heat, as waste heat. And it might not be a whole lot every year, but those kind of connections add up, so definitely take a look at those. I'm also looking to see if there's any overload situation on any of the lines. I'm not seeing anything there. You know, a single phasing motor may be operational and may be working, but you're going to see two of the phases significantly warmer than the one that was shut out, okay? It'll be a lot cooler, and that motor will start overheating. It will actually draw more power just to try to keep running. So definitely look out for things like that. No issues there. We're going to come up here now and we're going to take a look at the mechanical portion of the motor, the bearings. So once again, we're looking at the shaft end of the motor, and I don't see any issues. If I were to see an issue here with this particular bearing, it would be warmer than the rest of the housing. Usually, if something is 5 to 10 degrees centigrade above the temperature of the main part of the housing and it's on a bearing area, something's going on with that bearing. You need to do some extra work to try to figure out what's happening, because a misalignment, a bearing that's just wearing out, over lubrication, under lubrication, all of these things can also cause that motor and this motor pump assembly to operate inefficiently, draw more power, and not actually get the work done that you want it to do. So everything looks fine there, not seeing any issues. All right, you have to be a little bit careful when you're taking a look at couplings and shafts and things like that, because they tend to be a shinier metal, a lower emissivity material. So sometimes you can get reflections off of them that aren't really there and aren't indicative of the actual heat. In this case, I'm not seeing too much going on. I see a little bit of extra heating around, on the motor side of the coupling, but that could be an emissivity issue. I don't really know at this point. I'm not seeing anything significant, and because I'm not seeing any excessive heating on the bearing of the motor itself, tells me that more than likely the alignment's probably pretty good on here. So we're now going to take a look at the pump side and the pump. Don't see any issues here. I think this is operating really well. Any of these problems that I've discussed before is a great opportunity to say, okay, well, what do I do next? I've discovered something that may be draining energy, draining money out of my budget. How do we fix it? Well, you have to be able to diagnose it. So a lot of things, if you're finding a problem with a thermal imager and it looks like it's a bearing related or coupling related, you can then use a vibration tester. From an electrical standpoint, you find a high resistance connection or something looks like it might be overloaded, you can use a clamp meter. If you're finding problems that are localized hotspots, might be a problem with internal windings, it's a good opportunity to use the power quality meter. It could be, as I said, transients, harmonics, anything like that. All of these tools work together in conjunction to help you better maintain your equipment and save energy over the long run. I hope this was helpful to you. As you can see, it's not rocket science. Anybody can do this. You can start saving money and frustration today.